Well, hello and greetings from Northern Michigan. This is Bob the Science Guy. Today I have kind of a hybrid episode for you. Normally this would be under Northwood Scientists, but since this is such a buzzword in the flat earth, I thought I'd put this under the flat earth as well. You know, the other day I was looking at perspective and I was looking at demonstrations of curvature on the earth, and I used this water level. Notice how the water level is eye level, yet the horizon drops below the eye level. But that's not what I'm going to talk about today. I'm going to talk about this. Watch the image. Simply by rotating my iPad, I can rotate that image. Now, in the flat earth, everybody seems to think that this is all density and buoyancy. Why don't you explain to me how this is density and buoyancy, and then I'll tell you how it actually occurs. And guess what? It's due to gravity. So, let's cue up the music. Well, folks, say hello to my little friend, the BMA 280 Digital Transaxial Acceleration Sensor from Bosch. One of the many properties of this rather remarkable little chip is that it can sense the direction of gravity and use that to determine its orientation in space. It does that using a little bit of math, but the bottom line is it always knows where the center of the Earth is. And what's more, if you take this device on a swing or a merry-go-round and put it under a different type of acceleration or through an airplane or on a car, it'll measure those readings in addition to the force of gravity. Let's see what I'm talking about. So here's my setup. Here's my iPad sitting on my desk in my office. Now I've got a program on there called G-force meter that will read the output from that accelerometer in all three axes. If you look at the long edge of the iPad that's on the ground right now, you will see that that is the y-axis. And if you look at the direction of gravitational force going straight down perpendicular to that, that's the x-axis. The x-axis goes along this short edge here. Now the z-axis goes from the front of the iPad to the back. Let's have a look and see what that means. Now let's have a look at my high dollar illustration of an iPad. We have an iPad here and we've got the little button on the bottom edge. Now if we look at this short edge, let's call that the x-axis. We'll call the long edge the y-axis, and front to back, we're going to call that the z or z-axis. Okay, now that we've set up some directions on the iPad, we can make a coordinate system from that. We can have an x, a y, and a z-axis. The only other thing that we have to do is decide what's plus and what's minus. So taking the central point of each axis, let's go ahead and make down along the y-axis negative, left along the x-axis negative, and back along the z-axis negative. Okay, so here's our iPad and it's laying on the desk. This is towards me, this is towards the far side of the desk. It's laying flat, so the force that is acting on this iPad is moving in this direction, going straight down through the iPad, and that is in the z-axis. And since it is going in a negative direction, we're getting negative 1 g. Now, when we rotate the iPad so that it's like this, and it is going straight up and straight in the front to back z-axis, what we're going to do is we're going to have all of the force of gravity going straight down this way, and that is the x-axis, and it's in a negative direction. Now, if we were to lay the iPad on this edge right here, the gravity acceleration would be going in that direction, and we should see 1g in the plus direction. So let's go ahead and try that out and see what we have. Okay, so right now I've got the iPad laying flat on the desk, and the button is to my right, and the long axis is facing me, but again, it's laying flat on the desk. So we see the z-axis, which is the front to back axis, is reading negative 1g, and there's a total up in the white line up there of about 1g that is acting on the iPad. Now, this is what we would expect. Because it's going from the front to the back, that's in a negative direction on the z-axis. So it's reading the full force of gravity as a negative 1g in the z-axis. Now you notice up here that the green line, which is the y-axis, is reading 0. But the red line actually has a little acceleration due to gravity on it. What do you think that would be? It's because the iPad is slightly tilted due to the case. So if I bring it a little bit more level, you see how the red line goes straight back up to 0? And then if I bring it down, even though it's only about 1/10 of an inch, you can see that that makes a difference. Now, let's bring this up and put it resting on the long axis and see if we can kind of keep it more or less straight up and down, and it's resting on my level desk. So again, we have 1g total in the white line. If we look at the green line, which is the y-axis, it's resting on my level desk, so it's reading 0. And in the z-axis, which is the front to back axis, it's a little bit off. So what we need to do is we need to kind of square that up a little bit. Now it's completely vertical, and you see the green and the blue lines are covering each other. The red x-axis is reading -1 gravity because the force of gravity is going from right to left in the negative direction. Now, recall we said in order to change this, if we flip the iPad over and rest it on the opposite long side, even though the screen switches, we have a change in the direction of the red. Notice that the red now is underneath the +1 total gravity white line because it's experiencing 1 plus gravity. The green and the blue y and z axes are reading 0. Now if we tilt it slightly, we can bring those lines apart. Okay, let's see if we can make some sense of that. So we have the iPad resting at some angle above my level desk, and there's an angle there. Okay? Now, the force of gravity is going straight down in that direction. Now, right here we can see that in the z-axis, there is some degree of force going backwards. And in the x-axis, there is some degree of force going downwards. In the y-axis over here, we said that was 0 because it was just resting on my level desk. It wasn't tilting one way or the other. So how's this work? Now, if we make a graph, we know that the x-axis out here and the z-axis here. we know that it is going to be moving down in some direction in the z-axis. And we know that it's going to be moving in some negative direction in the x-axis. So if we plot these out, like so, we get a resulting vector that goes like that. Now, we know that this vector right, the green vector, is gravity. And we know that in order to get an angled vector like that, we have to have the iPad slanted at some angle. Now, where would that angle be? That angle would be right here. So, that angle would also be right there. So we can solve for that. Now let's go ahead and read off our numbers again. Now if we look at our numbers here, we see in the x-axis we have a negative 0.86, and in the z-axis we have a negative 0.52. So we'll go ahead and take our numbers and we'll put it in the right triangle calculator from Math Portal. So we have leg A, which is in the x-axis, will be 0.86, and leg B, which is in the z-axis, 0.51, and we're going to solve for angle A. Let's see what it comes up to. 59.33 degrees. Now let's compare that to reality. Now again, not absolutely perfect, but considering it's kind of a crude measurement that we're doing and we're just using a roofer's square, I think that's pretty close, don't you? Well guys, thank you very much for having a listen to that. I think that it is quite clear from these, which are the actual data sheets from the manufacturer. This is the BMA 280 data sheet, page 34. I think it's pretty obvious what this thing is sensing. It's not density. It's not buoyancy. If you try and continue to claim that density and buoyancy is responsible for the acceleration of gravity, which we have measured, we've observed it, we've used it to predict things, you're just being intellectually dishonest. This is the end of the flat Earth denial of gravity. Here is an actual instrument that measures gravitational acceleration that is present in all of our iPhones and iPads. Now, if you want to confirm this for yourself, that you are indeed actually measuring an acceleration, it's pretty easy to do. Let's go ahead. Get you on up here. You can get this program right here. You can measure the acceleration of gravity. Now, you can tell from this graph that we are undergoing a downward acceleration. We can see that this graph will demonstrate acceleration from any cause. For example, if I slide the iPad to the side, I get a change in my y-axis. If I bring it back the other way, I get the opposite change. This can be placed on a carousel or a merry-go-round. You can drive it around in your car and you can measure out the acceleration forces acting on your iPad in real time. It's simple to do. So stop making the excuse that you cannot accept gravity, because if gravity actually existed, it would mandate the Earth collapse into a spherical shape, which is the most efficient form for a body undergoing the effects of gravity, and start acknowledging the fact that it's right here. Now, either you can refute this evidence or you can accept it. You cannot refute it, so therefore you really have no choice but to accept it. If you refuse to accept this evidence of gravity, which is present in every one of our phones, then quite frankly, that's simply intellectual dishonesty. So, thank you all very much for listening. This is Bob the Science Guy. I hope you take a moment to like and subscribe to my channel. I have a long ways to go to catch Conspiracy Cats. He's got 22,000 subscribers. I only have 8. So help a brother out here. So, thank you all very much, and you take care.
This rabbit hole's too deep for me. Feel my brain getting real sore.